let us discuss orthogonal property of Legendre polynomials. And of course, we know orthogonal property clearly implies that there will be two solutions. There must be two polynomials. So we are going to have as m as one polynomial, we are going to insert this Pn of x, and we are going to have another polynomial as Pm of x. To learn orthogonal property, we need to have at least two polynomials, whether they are perpendicular or not. So this is one property of Legendre polynomial which we are going to discuss now. Orthogonal properties of Pn of x. So when minus 1 to plus 1 integration Pn of x dx equal to 0 when m is not equal to n. When m is equal to n, the answer is 2 divided by 2n plus 1. So this is your orthogonal property of Legendre polynomial. We can write this in terms of canonical delta function as like this. Okay. So now integration minus 1 to plus 1 Pm of x, this is one polynomial, Legendre polynomial. Pn of x is another Legendre polynomial which is equal to 2 divided by 2n plus 1 canonical delta. This is actually here you must have del mn. Here there must be del mn here. Okay. That is 2 multiplied by 2n plus 1 times del mn. If del mn equal to 0 when m is not equal to n, when del mn equal to 1 when m equals n. So this is 2 divided by 2n plus 1 times del mn. Okay, it's missing there. So together we can write. Now we are going to prove the Legendre differential equation. We are going to prove orthogonal property using Legendre differential equation. So this is your Legendre differential equation. Okay, very simple. We know already. We studied earlier. So earlier it was as n. Now we have inserted as L. Doesn't matter. L is a constant here as far as mathematical physics is concerned. Okay. So this is our equation. Now this equation can be written as like this. This equation, look at the first two terms. I have written as a single term. See here, this is first term, this is second term, this is your third term. First two terms can be written as a single term in this equation. I repeat, you just differentiate this. Okay, you differentiate this. Keeping this as constant, you will have to differentiate. Plus, keeping this as constant, you will have to differentiate this. Keeping this as constant, you will differentiate, you will get the first term. Keeping this as constant, when you are differentiating, you will get the second term. So we can write these two terms, yes, exactly like this. So two terms can be replaced with single term. Is it okay? Very simple one. I repeat, keep this term as constant, you will have to differentiate. Then keep this term as constant, you will have to differentiate. So 0 minus 2x, you will get this. So these two terms can be replaced with a single term, exactly like this. Now we are going to have two solutions now. One is Pn of x, another one is Pm of x. And y equals Pn of x is one solution, and y equals Pm of x is another solution. Now you substitute here. So d by dx of 1 minus x squared, instead of y you have to substitute Pn of x. So dPn by dx plus n into n plus 1 Pn which is equal to 0. Now you will go for the second solution. So you are going to substitute substitute y. For y you are going to substitute Pm of x. Okay. So one is Pn of x, another one is Pm of x. The same thing. Otherwise it's same thing. See here it is n into n plus 1. Here it is m into n plus 1. Now multiply equation 4 by Pm. Multiply this equation by Pn. You multiply this equation by Pm of x. You multiply this equation by Pn of x. So first we will multiply the equation 4 by Pm. So Pm multiplied by this term plus n into n plus 1 Pm which is equal to 0. Now multiply this term by Pn of x. See here Pn of x d by dx 1 minus x squared dPm by dx plus m into m plus 1 Pn which is equal to 0. You subtract this by this. 6 minus 7. 6 minus 7. So you have 6th equation is here minus 7th equation is here. 6 minus 7. Is it okay? This is your 6th equation. This is your 7th equation. Now I have taken this term here, first term, and I have brought this term here. And I have clubbed together this term and this term as exactly like this. Taking P and Pm out. common out. Take, see here, Pn, Pm, Pm, Pm. So we can write Pn, Pm out, n into n plus 1, and minus is here. So this must be minus m into m plus 1 equal to 0. Is it okay? So that's minus sign is missing here, correct? We will have minus sign. See, because we will have to subtract. So this is a minus sign. Here must be, there must be minus sign. So that's why we have minus sign here. Okay? So there's a mistake here. It's a minus sign. Now integrate with respect to x with the limit minus 1 to plus 1 on both sides. So now we are going to integrate. So this is your integral equation. This is your integral equation. This is your integration. I can pull n into n plus 1 minus m into m plus 1 out because it is independent of x. Okay. So I can pull n into n plus 1 minus m into m plus 1 out. Okay. And this term I have written exactly same as it is. Now n into n plus 1 minus m into m plus 1 can be simplified as n squared plus n minus m squared minus m, correct? You multiply n into n, you will get this. Multiply m with m plus 1, you will get this. Now you just take n squared minus m squared, a squared minus b squared. So you have n plus m, n minus m, remaining term n minus m it is. Now you pull n minus m out, common. See here you have n minus m, here also you have n minus m, you pull n minus m term out. So that will give you n plus m, n plus m. Here it is termed as 1, so plus 1. See here you have a common term n minus m. So n minus m multiplied by, you have n plus m, this is plus 1, so plus 1. Now instead of this you can substitute this. Okay, so now we are going to substitute. See here we have substitute n minus m, n plus m plus 1 minus 1 to n. Now look at the left hand side, expressions for the left hand side. We can integrate this as UDV method. We can integrate this as UDV method. So we are going to consider this as U, we are going to consider this as dV. Totally, it will be totally as dV. If it is dV, what is b? B is nothing but 1 minus x squared dpn by dx. Correct? See here, your dV is totally d by dx of 1 minus x squared dpn by dx. What would be? B is nothing but this one will go off. So you have 1 minus x squared dpn by dx. So you have the first term u dv equals uv. So this is your u, this is your v, minus 1 to plus 1, limits you have to substitute, minus b du. Correct? So your v du, b is nothing but your, this is your b, du is nothing but you have to differentiate with respect to x. So dpm by dx. Similarly, you have to substitute, use this expression, the same method, u dv minus u, which is equal to uv minus v du, you will get this expression and this expression. This is for m and this is for n. Okay, see here, uv minus v du, uv minus v du. Minus, already minus is there, you have minus, so this will become plus. Remaining term, let it be like this. Any doubt? When you are going to substitute the limit, so this is your plus 1, this is your minus 1, surely this one will go off. This will become 0. And here also this will become 0. Okay, here also this will become 0. So you have only this term and this term alone. So we have only these two terms. Okay, however, when you are going to integrate, surely this answer also will be 0 when m is not equal to n. You have to substitute when m equals n for the first one, when n is not equal to m for the second one, you will have to substitute. So when m is not equal to n, this one will become 0 and this one will become 0. This cannot be equal to 0. Only possibility is this term is equal to 0. When m equals n, what is the answer? When m equals n, when m is not equal to n, answer is 0. When m is equal to n, answer is 2 divided by 2n plus 1. Correct? 2 divided by 2n plus 1. For that we will have to go with the lengthier process. So we are going to discuss now. Now we are going to discuss about if for m equals n using generating function of Legendre polynomial. We discussed earlier in the last video lecture about generating function of Hermite polynomial, which can generate the Hermite polynomial. Similarly, this function 1 minus 2xz plus z squared to the power minus 1 by 2, which will generate the Legendre polynomials. You have to remember this one. So this will generate first polynomial, second polynomial, when n equals 0, when n equal to 1, when n equal to 2. So this will generate Legendre polynomials. So you have to remember this. Now squaring on both sides. You just square on both sides. When you are going to square on both sides, left hand side becomes to the power minus 1. It's very simple. Whereas when you are going to square this term, it is not to the power squared. It is not. You have to be more careful because we will be using only two variables n and m. When you are going to square it, this becomes z to the power n pn of x multiplied by z to the power m pm of x. Very, very important in orthogonal property. When you are going to square it, we will have to use only the other index in orthogonal property. It is not exactly as it is squared. It is not like that. It is, see, for n times, this is p times. After squaring, you will get this. Okay, so we can write this as z to the power n, z to the power m, pm of x, pn of x after squaring. Now, for first case, when m equals n, when n equals m, this becomes z to the power 2n. When n is equal to m, this becomes pn of x whole square. Suppose when n is not equal to m, you will have to write as it is. So z to the power m plus n, pm of x, pn of x, this case. Okay. So now this is equivalent to these two terms. So now we will have to integrate with respect to x this time. As I said, that is equivalent to, this is equivalent to these two terms. So we have written this is equivalent to these two terms we have written. Now integrate with respect to x with the limits minus 1 and plus 1. So integrate. So now we are going to integrate. Now look at this term. When m is not equal to n, this term will become 0. You will have only this term alone. When m is not equal to n, this term already we have seen earlier in the first case. When m is not equal to n, this term will become 0. So this term alone will exist. So we have written right hand side like this. Now we are going to integrate this term. Okay, integrate. The integration answer will be exactly like this. When you are going to differentiate this term, you will get this term, correct? So this is what we learn. So now you just differentiate this. So differentiating, that will give you 1 divided by 1 minus 2xz plus z squared, correct? And you have to differentiate this. Differentiating with respect to x will give you 2z. See here, 2z. 2z. I repeat, see here, you have to differentiate this, you will get this. Okay, you must get. So differentiation of this one will give you 1 divided by 1 minus 2xz plus z squared. See here, 1 divided by. Okay, multiplied by, you have to differentiate with respect to x. So answer will be minus 2z. So minus 2z and plus 2z will get answer. You see, you have got integration. This is the idea. When you are going to integrate this, you will have this answer. When you are going to differentiate this, you should get the original one. So we have obtained the original one. Right hand side, let it be like this. So this is the answer. Now substitute the limits 1 and minus 1 for x. So you will have 1 minus 1 divided by 2 is log 1 instead of x 1. So minus 2 is plus z squared, and here it is 1 plus 2 is. You have to substitute minus 1 for x. So that will become minus minus plus. So plus 2 is plus z squared. This can be written as a minus b whole squared formula. This can be written as a plus b whole squared formula. Okay, now log rule says that you can bring this 2 down this side. 2 will get cancelled. Okay. According to log rule, so these 2 we can bring it to this side, and these 2 and these 2 will get cancelled. You have 1 minus 1 by z. A remaining term log 1 minus z. Here also you can have minus log 1 plus z. And this right hand side, let it be like this. So any doubt? Simple one. Now we know that log 1 plus z, the expansion, we can write this as z minus z squared by 2 plus z cube by 3 minus z to the power 4 by 4. And similarly log 1 minus z can be written as like this. But we need to have only minus 1 by z, log 1 minus z minus log 1 plus z. So we'll have to subtract 1 minus z by this one, from this one. Okay, is it okay? So we need to have this one. log 1 minus z minus log 1 plus z. So you have to see here we have log 1 minus z. Here we have log 1 plus z. So you have to subtract. So when you are going to subtract, this becomes plus. So z plus z 2z. This becomes plus, and this will get cancelled. And this will become plus. See here, plus. And this will become plus. This one and this one will cancel. So you have now 2z plus 2z cube by 3 plus 2z to the power 5 by 5 and goes on. The last term will be z to the power 2n plus 1 divided by 2n plus 1. And of course, minus sign we have taken, we have subtracted already. So minus sign will cancel, you have 1 by z. Either way we can do it. See here, suppose 1 by z multiplied by minus, just multiply with the minus sign. So this will become minus and this will become plus. If you subtract, the minus sign will get cancelled. Okay. Now this will be your last term. Now you pull 2 out. So you pull 2 out. So 2 by z plus z cube by 3 plus z to the power 5 by 5 dot 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 the last term. This term let it be like this. Okay, now I am going to multiply 1 by z. I am going to take 1 by z inside. 1 by z inside. So this will become 1. This will become z squared. This will become z to the power 4. See here, 1 by z. 1 by z alone I am going to take it inside. And z to the power 2n plus 1. Z to the power 2n plus 1 can be written as z to the power 2n z divided by z. That z and that z will get cancelled. You have z to the power 2n alone. So z to the power 2n alone. I repeat, see here, you have 1 by z. You bring 1 by z to inside. Okay, you will have z will get cancelled. Z squared you will get z to the power 4. And here z to the power 2n plus 1 can be written as z to the power 2n, z to the power n. Z to the power 1 divided by z. This z and that z will cancel. Here z to the power 2n. And the right hand side let it be like this. Okay. Now equating the coefficient of z to the power 2n on both sides. Here z to the power 2n. Here z to the power 2n. So we can equate the coefficient z to the power 2n. So you have 2z to the power 2n divided by 2n plus 1. See here. This is z to the power 2n divided by 2n plus 1 multiplied by 2. We are going to equate the coefficient of z to the power 2n on both sides. So this is your coefficient 1 divided by 2n plus 1 multiplied by 2. This is your coefficient of z to the power 2n. The coefficient of z to the power 2n is nothing but this one. So the coefficient of this one will be, this one is equivalent to this. So 2 divided by 2n plus 1. So we have now minus 1 to plus 1, 3n of x square dx equals 2 divided by 2n plus 1. So this is of the second one. When m is not equal, when m is equal to n. When m is equal to n, answer is 0. M is not equal to n, answer is 0. When m equal to n, the answer is 2 divided by 2n plus 1. Combinedly we can write, see here written correct. Correctly we have written del mn. When m is equal to n, answer is 1. When m is not equal to n, answer is 0. So this is what orthogonal property goes. Okay, very simple one. It's very important one. The orthogonal property of Legendre polynomials. So we have taken as n and m, pm of x and pn of x. Okay. Now generating function of pn of x.